All right, this is just a quick summary lesson of investigation, or section 6.2, which has lots of little investigations. Just a quick review from today in class. We talked about tangent properties, but we also talked about minor arcs and major arcs, and the fact that this little lowercase m means measure in terms of degree, and it comes up throughout the chapter. So just wanted to remind you of that. And then the other property we talked about was that the tangent intersects the radius at the point in tangency at a right angle. And those properties you need to know to do the new things today. So we're going to just start with chord properties. Just a quick vocab reminder also that inscribed angles have their vertices and their endpoints on the circle. So an inscribed angle has a vertex here, and its endpoints have to be somewhere on the circle. But a central angle, just like it sounds, has its vertex at the center. So that terminology is used throughout the chapter. But there's also angles that are neither inscribed nor central. And all of these angles here, angles 1, 2, 3, and 4, are just other angles in a circle. And we'll be using those this chapter too. But because they don't have their center at the circle or on the circle, we just talk about them as other angles in a circle. Okay, so the new stuff. In investigation 2, in section 6.2, there's a variety of investigations, and they're really quick, and so I thought we could just summarize them at home, and then you could come to class and work. So looking at the investigations, this first one just says if two chords of a circle are congruent, then they determine two central angles that are, and then you just have to fill in the blank. So I've made a picture here where you can see the two chords in the circle are both 2 units, and you're supposed to determine how they relate to the central angles that are in the circle. So, in other words, if you just drew in central angles to the two chords, how would these central angles be related? And let me fix that one a bit. So if I look at this as angle 1 and that is angle 2, what can we say about them? Well, hopefully you've thought about it. If the chords are congruent, we can use markers to identify them as congruent. And the central angles, by definition, are formed by radii, so all of these are congruent. So I have a triangle here. We'll call it triangle A, B, we'll make this point C. So this first triangle, A, O, B, has to be congruent to the second triangle, C, O, B, by side, side, side. So since the triangles are congruent, we would then conclude that angle 1 has to be congruent to angle 2 by corresponding parts. So, in other words, if two chords in a circle are congruent, then they determine two central angles that are congruent. And that's that whole investigation. Okay, or that whole conjecture. So this next conjecture takes the same picture if I zoom out, but it's asking if two chords in a circle are congruent, then now you have to fill in this. but it's the chord arcs conjecture. So what we learned from today in class is that if this angle was, say, 65 degrees, then that angle would have to be 65 degrees, because the central angle always has the same degree measure as the intercepted arc. So if angles 1 and 2 in this picture above are congruent, then we would know that arc BC and arc AB would also have to be the same, because they would have the same angle measure. So, in other words, without drawing all those triangles, if you know that this angle is or this segment's congruent to that segment, then you know that this arc from point A to point B has to have the same degree measure as the arc from point B to point C. In other words, if I told you that this arc AB was, say, 85 degrees, then you would conclude, because the two chords are congruent, that arc BC would also be 85 degrees. So we say they're intercepted arcs are congruent. And the term intercepted arc just means if you have a chord, say this one here, and I extend the line, the piece of the circle that it cuts off. So the piece of the circle that's cut off right here, that's the intercepted arc for chord BC. All right. Next investigation. So in this investigation, we're looking at the perpendicular, so the blue line, to a chord, and what that relationship is. So you can see, because this is a square edge on this ruler, that that's a right angle. So this is the perpendicular segment. If I label this A, AB, we'll call this circle O, and circle O intercepts AB at point M. The perpendicular that I'm looking at is segment OM. OM is perpendicular to AB. And when that's true, how is it related to the chord? So again, you could go back to all of your chapter 4 information and construct two triangles using radii. And we know that the same segment property combined with the definition of a radius gives us two triangles with a leg and a hypotenuse congruent. And today in class we talked about the hypotenuse leg conjecture. Which tells us in a right triangle, if you have one pair of congruent hypotenuse and one pair of congruent legs, you know the two triangles are congruent. So we know that triangle AMO is congruent to triangle BMO by the hypotenuse leg conjecture. And because of that, we know that AM is congruent to MB by corresponding parts. So in other words, if you have a perpendicular, this perpendicular segment from the center to a chord, not only is it perpendicular to the chord, but it's the perpendicular bisector of the chord by corresponding parts. So that's the missing term here. And this last bit here, two congruent chords in a circle are blank from the center. So if we know we've got two congruent chords right here, and we look at the title, this is the chord distance to center conjecture. Anytime we want to measure distance, we measure along the perpendicular of a, because perpendicular is the shortest distance. So if I took this and went at a right angle to the chord, just like we did above, I can use this corner of the ruler here to get a square angle. That distance looks to be about 1.1 units when you look at this distance right here. So if I do the same thing, let's write that in. This is 1.1 over here, and again using the square edge of the ruler to get a perpendicular distance. That's also 1.1 units going along this line here. Whoops. Let's erase that. There we go. A little bit messy there. But in this picture, this is also 1.1 units. So these distances are congruent to one another. So the chord distance to a center conjecture, if you have two congruent chords in a circle, they are equidistant, or the same distance. From the center. All right. Not super very exciting stuff, but remember the whole goal of this first couple units is to get you to solve big circle problems, so you need all the little pieces. This is the last little piece of section 6.2. If you have a perpendicular bisector of a chord, it should pass through, what do you guess? If I have the perpendicular bisector of the chord, what's the missing word there? So I'm just going to create a perpendicular bisector by going a little more than halfway. Remember, you do have some constructions that you have to keep up with in this chapter. So I just did a quick perpendicular bisector of a chord. And if I draw that in, oops, with my tool, my straight line tool, it should pass right through the center. All right, so those are the summary statements of the investigations. Here's a couple quick practice problems. Let's take a look at these. Penta is a regular pentagon, so that tells us all equal sides, also all equal angles. It's inscribed in a circle, that tells us all the vertices are on the circle. That's what the term inscribed means. So the measure of PE, well, we know the measure of PE would be 360 divided into 5 congruent parts. So each of those parts would be 72 degrees. And since the chords are equal, all of the other measures are 72 degrees. This number problem 2, we have 2 congruent chords. So if the chords are congruent, the intercepted arcs are congruent. So if this is 140, this over here is 140. So 140 and 140, when you add them together, you get 280. So the remaining degrees would be 80 degrees. So that's the measure of this arc. And therefore, if the arc is 80 degrees, the central angle associated with it is also 80 degrees. And then this last one's actually a chapter 3 problem too. It's asking you how you would explain how you would locate the center of the circle that contains arc AB. So if you think about this problem and look back, say at one of these pictures, right here, for example, we know that the perpendicular bisector of any chord passes through the center of the circle. So if you look at this one, it's the same thing. The perpendicular bisector of the chord passes through the center of the circle. So down here, you can just create